Hello again. We are going to be starting the new chapter and the part called the derivative. So before I get into any kind of actual mathematical description of it, I want to show you what it looks like and how we then can use it and how it is actually a rather simple, elegant idea. So I've set up a simple function. We have a second degree here, and with some of the other films I've made, we know how to solve them. You can look right on the intercept for x. But now we're going to be doing something a little more interesting. We're going to take the derivative, but we're not going to do it mathematically first. What we're going to do is first I'll describe what it is and what it looks like, and for that I need to draw a new line. So this yellow line here, the one that is attached to the purple, and you can see it hits it right about here, and it is a tangent, which means, even if you can't really see it because this resolution isn't the best, it touches the curve at one spot and one spot only. And it builds a 90-degree angle with the part of the graph that it touches. So the derivative in this case for a particular place on the curve is this yellow line. And this yellow line has a slope. And you can remember from Math B that the slope, or lutning, is the rise, the height of the triangle, divided by the run, or the base of the triangle. Remember the k equals delta y over delta x. So the slope of the tangent is what we use for the derivative of the purple function here. Now let's take a look at another one. It's the same function, but I've put another tangent line on. And this time the tangent line is kind of turquoise in color. And it's over here on the left. I had it touch here at the -2 place. It doesn't have to be there. I could put a tangent here, could put one here, could put one there, and the lines that would be attached there would just follow the curve. Some would be a little more like this, and some would be more like that, and so on. So the idea is rather simple. Mathematically, it can be interesting later when we go through the definition and then the rules and how do you do it and what can you use it for. But the idea is really rather simple. When you have a function and you take the derivative for a particular place on the function, you're going to end up with a tangent line there. And the tangent line has a slope. The slope is just like it's decided like any other Math B linear function. You have your you have this here, and the k value of the line, and all lines have them, will be the derivative of this purple function at the place that you choose. We could choose there, or we could choose there, we could choose there, or there, or there. It gives us different lines, and the different lines have different slopes. And the slope is what we get. That's what we're after most of the time. So now here I have some other lines. I just wanted to illustrate that every line, including tangent lines, they point in a certain direction. And they will have a slope. And you can draw your little triangle and you can count out your delta y and your delta x. And this one has a slope. Now this one is pointing in a different direction, but a line always has a slope. This one is flat, and it'll have a slope of 0. This one, going from left left to right like this, it will have a slope that is negative and goes down. So all lines have slopes, including tangent lines. And the derivative will help us find the k value, or the slope, or the lutning of those lines. And then when we go through the definition, we'll be able to see how to use it, how to actually take the derivative mathematically and algebraically. And after we learn the rules, we won't have to use the definition anymore to take the derivative. We'll be able to use the rules because the rules were based on how the definition works.